Students, welcome to your video about the solar system mechanics, as in the movements, motions, the literal how does this machine work. First, we're going to talk about Kepler's laws of planetary motion. Then we're going to go through. So starting with Kepler's laws of planetary motion. Kepler is a guy you've heard mention of before. He did a lot of stuff. This is one of those things. So his first law of planetary motion is that all planets have an elliptical orbit. An ellipse, as in fancy nerd speak for oval. The orbits of planets is oval. They have two foci, rather than, just for point of reference, the orbit of a planet, any planet, not just Earth, not just the 8 in our solar system, but any solar system, they are not perfect circles. It is not a radius whereby that would be the planet is the same distance from its star all year round at all points in its orbit. That is not the case. Instead, the planet's orbits are elliptical. There are two foci. That gives us something called the semi-minor axis, is when a planet is closer, and a semi-major axis when it is farther. We do not need you to know those terms, semi-major and semi-minor axis, but I want you to be aware that semi-major axis is the data point you're going to see written into some of our apps and whatnot, and it's referring to the distance that planet is from its sun. So effectively, semi-major axis is the distance from the planet's sun. All right, but from this, make sure you understand there's a time in the year when a planet is closer to its star. There's a time in the year when it is farther. And just FYI, in our particular solar system, both of the foci for, whoa, what did I just do? Both of the foci for our planet's orbit are in the sun. Our particular Earth's planet's orbit looks very close to circular, so we can't really tell a difference, but that definitely makes our sun the center of our solar system. That is also true for the orbits of the other of the 7 major planets. As it just so happens, Pluto's orbit is more elliptical. That's not what makes it a dwarf planet rather than a planet, but that does happen to be true. Okay, the second law of Kepler's planetary motion is that planets move faster when they are closer to the sun. Think about this for a second. When is Earth closest to the sun? Your gut reaction is going to have you saying in the summer, in June, July. It's actually in December, January. And this has to do with the hemispheric tilt, the planetary tilt, and so hemispheric seasons versus planetary seasons. But as it so happens, the entire planet of Earth is closer to the sun in December, but our northern hemisphere where we live is pointed away. So it's winter for the northern hemisphere, but it's actually summer for the southern hemisphere. So the true planetary summer is in December. Well, actually it's January, but anyway, and then June, July is the true planetary winter. Okay, a couple of connections here, a movie connection. We will be watching the movie The Martian, and this character, you may know him as Childish Gambino or from the show Community, but anyway, he's in the movie, and he talks about this gravitational slingshot, which basically what they're going to have the crew of is it Ares? Yep. Of the Ares mission do is get a gravitational slingshot around Earth to head back out to Mars. And it's kind of like Mario Kart when you go over the, they're called the the boosters. Anyway, you just, the pew, it's kind of like that. All right, but anyway, the planets move faster when they are closer to to their sun. Okay. The third law of planetary motion is that the time it takes for a planet to orbit depends on its distance from its sun. In other words, a larger distance is a longer orbit. So like runners on a track here, the one in the closest lane has the shortest path to go, and so it would take less time. The runner in the farthest out track has a longer distance. It takes more time. In our solar system, that is, for example, Mercury has a semi-major axis of 0.4 astronomical units, and it takes 88 Earth days to orbit. Neptune is the farthest one out there at about 30 astronomical units, and it takes 165 Earth years for Neptune to complete one orbit. All right, before we move on to the next set of notes, I want to explain a little bit here about space and time, space and time. Space and time are interwoven in outer space. This here, this image, is an exaggeration of our orbit, of the orbit of Earth. And you can see the months marked. I also just want you to take a moment to notice the pie slice here from January to February. It's a longer arc, but a chunkier looking pie slice, whereas the month of July here, it's a smaller arc, but a bigger chunk of pie slice. If you took this, a narrower pie slice, if you took this to a geometry teacher, you could get the equation for the area of each pie slice, and they actually are all exactly the same amount of two-dimensional space. And that's why the months have, like for instance, why February is only 28 days long, because this pie slice only equates to what is 28 days. Whereas October over here, that equates to 31 days, and so on and so forth. But take a look at this. That's the month of December. Here's the month of January. And in terms of time, we think of December, we experience it as time. But to the planet, this is a location in the orbit, as in it is space. Space is location. It is space to the planet. It is time to us. Space-time. So keep that in mind. October 9th is my birthday. I think of that as a time, but it is a specific place in our orbit to the planet. Now, this is true for any planet. We just don't call it March, April, May, and so forth. There would be other names, or there wouldn't even be months. But I want to make sure you have that understanding that location in the orbit is what we would think of as time. All right, moving on. The amount of this that we see. This is an exaggeration. It's never this much like an oval. But when it is, there is a time of the year in which the planet is closer. There's a time of the year at which the planet is much farther. So think about that. When it's more like a circle versus more like an oval, what will that change? It's real easy to see that here. There could be, all right, here's planetary summer, here's planetary winter. In an extreme exaggeration like this, we would have winter like from April to October. That's not the case right now. Our seasons are pretty evenly 3 months of the year, as opposed to 1, 2, 3, 4, 5, 6 months of the year. Planetary positions and what that means. So planetary positions, periodic motions, and how these things relate to climate. Now, these are called, several of these motions are called Milankovitch cycles. You're going to use this simulator in class, and if anything, I want you right now to go ahead and pause the video and open up that simulator. So here's that simulator, and you can see the options we have here. Some of these terms I'm about to teach you with eccentricity, precession, and a couple different things about the tilt, which obliquity, anyway, we'll get there. You're going to be doing a lab that pertains to this particular simulator, and so you should come back and forth looking at this as you go through what I'm going to be teaching you. All right, so the first periodic motion of Earth is rotation, which is spin. Rotation is the official term. No one calls it that. Just from here on out, it's spin. I just want to give you guys warning. You might see it written as rotation. You can see that it is spinning because of all those push pins I just stuck in here. And now, what is it that we experience on Earth because of the spin? Night and day. You know that. And how long does it take Earth to spin once on its axis? How many of you said 365 days? It's 24 hours. Revolution is the second periodic motion. Revolution is the nerdy word. Everyone just calls it orbit. But again, if you see revolution, we're talking about orbit. But all right, orbit. The planet orbits around its star, well, in a solar system with only one star, but you understand what I mean. The planet orbits. How long does it take Earth to orbit? It takes 365.24 days, another Earth days, by the way. In other words, one Earth year. That 0.24, by the by, is the reason we have leap year. So let's say that this pipe cleaner represents January 1st, like midnight on January 1st. Now, if we did not have leap year and the planet were orbiting the star 365 days, year one, it would only get like this far. It wouldn't quite finish its orbit. In year two, it would be half a day behind. Year three, it would be 3/4 of a day behind. Year four, it would be a full day behind. And year after year, we would still just not quite complete our orbit. So every 4 years, we have February 29th, that leap year, to make up for that 0.24. Okay, now I want you to notice right now how this data table is set up. It's very intentional, bold lines, dashed lines, and these things are tabbed in. This stuff in here refers to the orbit. The eccentricity and inclination are two characteristics of the orbit. Down here, we're going to talk about tilt. These two things, obliquity and precession, are characteristics of the tilt. So bold lines, these things are about tilt. Bold lines, these things are about the orbit. All right, so about the orbit, moving on from here. The eccentricity is the change in the shape of the orbit. This is like the orbit going wah, 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 wah. As the orbit goes from more like an oval to less like an oval and more like a circle. Now, it never gets perfectly circular because Kepler's first law of planetary motion, the orbit is never perfectly circular. But anyway, it's given in a value of 1, most like an oval and least like a circle, to 0. An ellipticity of 0 would be a perfect circle. This change, our Earth's eccentricity, changes within a range from a minimum of 0.005 to a maximum of 0.0607, and it takes about 100,000 years for that to happen, meaning at year 0, maybe we're at this minimum. 50,000 years later, we might hit that maximum, and another 100,000 years later, we'd be back to that minimum. Now, it's not a perfect exact every 100,000 years, and we don't hit this minimum every single time. We don't hit that maximum every single time. But anyway, here's where it's most like a circle. There's where it is least like a circle. Currently, our eccentricity is 0.0167. As far as a range for planets, for you to know, an ideal range for this is going to be less than or equal to 0.106. This is a fairly small range. And where that number comes from is if you look at the orbits through the Exoplanet app, you look at the shape of the orbits, looking at the kind of cartoon version of it, right here it still looks like a circle. Once it's 0.0107, it noticeably looks like an oval. So that's not an official range. That's just eyeballing it with a bunch of different students over the years and myself. All right. Now, what this does, I want you guys to think about this for a second. This would be changing, well, we got changing the length of the planetary seasons, not hemispheric seasons, but the overall planetary seasons. So when it's more like an oval, there will be more time that it spends farther away, and so longer winters, versus more like a circle, there's less of a winter. All right, and this eccentricity could define the seasons if the tilt is 0. If there is absolutely no axial tilt, this would be what would define planetary seasons. And this is where we are right now in our current research of exoplanets, because we can know the eccentricity, but we cannot know the axial tilt. So this is as good as it gets for now in terms of knowing whether or not something has seasons. All right, the other thing about the orbit, the orbit could be the tilt of the orbit, which is called inclination. This is not the tilt of the axis, this is the tilt of the orbit. So what this is if this is the sun and this is the planet, this is the tilt of the axis, not what I'm talking about. I'm talking about the tilt of the orbit. So this would be an orbit with no tilt, no inclination. This would be an orbit that is highly inclined to like all the way like this, a highly inclined orbit. So inclination is the tilt of the orbit. And on this one, we really don't have a whole lot of information about what this means and everything, but our current orbital tilt is negative 0.005. The closer to zero, the better. Maybe this is the good range. There is not research and information out there yet to give us an exact idea of what does this do. But here's a hypothesis I'm going to give you, and hopefully plant some seeds of one of you who's going to grow up and make a doctoral thesis out of this. Anyway, what this does, like P1 here, is a planet with an inclination of 0. So an orbital tilt of 0, it orbits perfectly in the equatorial plane of the sun. Well, these lines you may recognize, this is imaginary lines indicating the electromagnetic poles of the sun, or of whatever sun we are talking about. So if we have a planet like P2 here that's highly inclined of its orbit, what's going to happen when it's at this point in its orbit? What's going to happen when it's down here in this point in its orbit? This is going to change the impact of the electromagnetic radiation it receives from its sun. That could do some weird stuff. All right, now we're moving on to the axial tilt. This one is tilt as you think of it. This is star, planet, tilt. Now also think about this. In space, there is no up, down, left, right, north, south, east, west. It all has to be a reference to something. So a planet's axial tilt is relative to, we normalize the star as being a tilt of 0. How far off is it tilted from there? Right now, Earth's tilt is at an angle of 23.5 degrees. Now, the result of this, well, the northern hemisphere would be experiencing what right now? Winter, because it's pointed away, whereas over here in our orbit, the northern hemisphere would be in summer. So this gives us what we call hemispheric seasons. The angle of the tilt can change, and that is something called obliquity. Vocab. I'm sorry, guys, but that just is what it is. The obliquity. But that's a change in the tilt of our axis, and our axis changes with an angle of as little as 21.5 to as much as 24.5, and we're currently at 23.5 degrees. And this happens every 41,000 years. It's not a perfect cycle, like it's not exactly 41,000 years, that's an average. It doesn't necessarily go to a minimum of 21.5 every time. It doesn't necessarily go to a maximum of 24.5 every time. Check that out in the simulator. The simulator up here that we've linked to. You can see that change over time and how it sometimes hits the minimum, sometimes the maximum, and so forth. Now, what is that going to do? I want you guys to think of this one on your own. Here's the tilt. If I increase the tilt angle, what does that change about the northern hemisphere's winter at that moment? And what would it change about the northern hemisphere's summer? If the summer looks like this, it's like, oh, here we are at about 23.5. If we're way over here, what's that going to change about the experience of summer? Now, I know you can figure that out. And I know you figured it out in that it's It's this. It's what we call severity of seasons. How severe are the seasons? A big tilt angle, very cold winters, very hot summers. A small tilt angle, less of a difference in the seasons. The last thing is precession. Precession is a change in the direction of the axis. Its nickname is wobble. Wobble, baby, wobble, baby, wobble, baby, wobble. Okay, anyhow, here's what that looks like. If this is, if I'm pointing out right here with the Northern Hemisphere, this is representing Northern Hemisphere winter, so representing the time of the year that we call like December, January. So if with a wobble, with a precession, that would be like this. So where we'd saying this is still the location in the orbit known as January and December, but hey, look at this. The Northern Hemisphere is now pointed towards the sun, and so that would change the timing of the seasons. And so then Northern Hemisphere would be experiencing summer in December, January. That is what the precession does. Okay, so that's what the precession does, changes the timing of the seasons, timing of the hemispheric seasons. I also just want to bring special attention right here. This says G moon, as in G subscript moon. The gravity of the moon helps to moderate the precession of the planet. So that's one thing about when we're looking at a planet, an exoplanet to go to, do we want a planet with a moon? Honestly, it is generally going to be a good thing because that can help to stabilize the climate to some extent, which perfectly segues us to climate. Why do these things impact climate? Climate being temperature and precipitation on an overall year-round, year after year after year after year basis. Well, all of these impact the distance between the sun and the given planet. The distance from its sun, its relation to its sun, what's that going to change? Temperature. So of course, and temperature drives the solar radiation drives the water cycle. So yeah, it's going to change precipitation as well. So all of these things impact climate. These are natural climate change factors. Okay, so then what kind of climate would a planet such as Earth have if the eccentricity, the obliquity, and the precession were all aligned to a solar minimum at a given time, as in receiving less sun? And I'm really simplifying it here. But if everything is solar minimums, dun dun dun, ice age.